assume that the money, the capital is distributed uniformly around the US or the US. And then the question that people are interested is that how this actually money will be concentrated on different parts of this map and what really affects the opinion of the individuals to go and invest in California, but for example not in the south, in the north. So this kind of question that how can we predict the outcome of formation of opinion of individuals is capturing opinion dynamic, and it has some applications in like political science, economics, and electrical engineering, because you can think of like a bunch of robots that you want to control them, that they concentrate at some points, and then you want to actually impose some formation to go and on the robots. So one of the models which is trying to actually capture this opinion formation is known as Hexelman class model. So the model is very simple. I'll just show in this example. You assume that you have n agents in a simple case on the plane, but it can be in d dimensions. So opinion of one agent is actually denoted as the location of that agent in the plane. For example, here we have 5 agents, and the position of that agent actually represents the opinion of it. So and each agent has a confidence bound epsilon, which actually he can only communicate with the people who are within his epsilon neighborhood. And at each time step, that agent takes the arithmetic mean of the agents which are in his neighborhood and moves to that location. For example, here, if this is the initial configuration, agent 1 takes the average of 1, 2, 3 because he can observe all of them, and then moves to this location. But for example, agent 5 cannot observe anyone within his neighborhood, and he remains here. So in the second time step, these agents move actually to the red points. And if you iterate it one more round, all the agents in the top will collapse to one single position, which is the green point, and this agent is isolated. So the question that they asked by Hexel and Kress, that how this dynamic actually evolves, and what's the actual termination time, how long does it take that this actually evolves, and so on and so forth. So these are actually important because despite its simple model, it's very surprising, it's very hard to analyze, because the state of the dynamic, the communication network actually is changing, and it really depends on the state of the dynamic. For example, the communication network is not fixed. Here, these 3 are connected, this is not, but once they cooperate with each other, the communication network changes, and then depending on which one is observing the other one, everything is actually changing and they are coupled. So if we can obtain some results on such simple dynamics, it can go beyond some scopes which actually generalize some of the earlier results that they assume that the network is fixed and agents are actually interacting with each other. So the existing result here is that the termination time of such dynamics, it was proved earlier in 2000 that it's finite. When we look at the agents in only one dimension, the termination time lies between n squared and n cubed. But in d dimension, the problem is more complicated because agents have more degree of freedom, and the best known bound was that this actually by some folks in Princeton, that the termination time is n to the power of d squared, where d is the dimension that these agents are lying. So in this talk, in this work, we actually remove the dependency on the dimension. We improve the bond to the n power of 8. And I'm not going to go through the proof techniques. But what's the game theory here that we apply here is that this dynamic that I explained has a very nice interpretation in a game theoretic model, because assume that, look at these agents as players of a game. So each player has a utility function which is defined to be this. this has a nice interpretation because assume that we have n players and the government gives them n minus 1 epsilon squared dollar. And the goal is that they have to build as many roads as possible between each other. So agents do not want to take risks because if a person is far from him, for example, agent 1 is here and this guy is far from him, he doesn't want to spend more than epsilon square budget to spend to build that road because he is far. But if it's less than epsilon square, he prefers to build that road and spend that epsilon square because if he doesn't, the government will take it back. So each player has actually this much money, and this is the amount that he is using to build the possible connection. So therefore, in total, he is actually saving this much. So that's the utility of it. But it can be shown that now if players play their best response, try to optimize their utilities, actually it captures the evolution of this dynamic, and anytime that one of the players is improving his utility, is playing his best response, that actually decreases a general potential function or Lyapunov function you can think of, and we can actually compute these decrements, how long does it take. So this is actually the simulation results that we have for 2-case and 3-case. Agents are around the circle at the beginning. So anytime that the dynamics evolves, they get closer and closer to each other, and at some points all of them collapse in the same point. But in 3 dimensions, for example, if we put them around the circle and some of them on the z-axis distribute based on some sinc function, after, for example, 10 iterations, they move to this red box, and if we iterate it like for 50 iterations, they actually group together in these red points. But simulation results show that actually the convergence speed is much faster than the upper bound that we have in 8, and it's a question that how can we improve it. And I just mentioned one very long open question here, is that it's actually for more than 15 years people are trying to figure out the evolution of this dynamic when agents have different radius of observation. It's not clear that does really this dynamic converge, and if yes, how long does it take? And this is known as the heterogeneous hexagon cross model, which is quite important actually to understand the evolutions. And that's all. That's what we have done. Thank you very much.